Hello, on behalf of TAS International, I'd like to welcome you. My name is Peter Rittmeyer. In this presentation, we're going to talk about the fabric material of airbags. Typically, an element is made of a part, an element, property, and a material. The properties for airbags are recommended to use MEM3 elements for that. MEM, obvious. They are not shell, they have hardly any bending stiffness. There is some bending stiffness, but membrane is the dominant part of it. For the property of MEM3, it's recommended to use strain form green. It's an objective formulation by default. It means that the way you number the elements, the nodes of the elements, is independent. Optionally, you can also use linear strain formulation, but then you have to use the co-rotation objective, because otherwise the node numbering of your elements will affect your results. In the picture here you see three strain formulations. As said, the green is recommended. It's a bit like an exponential curve. A linear is obvious, straight, and log is like a log. There basically are three types of materials to be used for airbag fabric. The simple one is isolin or ortholin. It's suitable for generic fabric modeling, but we prefer to use fabric shear. In the picture on this sheet, you see a simple isolin curve. In the tension direction, you see the E modulus. In the compression direction, the third quadrant, it looks a bit different. You see a reduction limit strain and a tension only on. And at the end you see the E modulus again. This is a numerical trick. In such a way you can mimic wrinkling. Ideally, of course, you would like to have a very fine mesh, but that will have a price, a very high CPU time. So typically the element mesh is about 1 centimeter. But that's not sufficient to capture wrinkling properly. For that reason, the reduction limit strain reduces the E in compression, and due to that you mimic the wrinkling effect. To prevent total collapse of your element, at the end you will get the E modulus back again. That's a user-defined parameter. On top of that you can define kappa. For typical load cases like passenger and driver airbags, this is not that relevant, because the energy loss through to heat transfer is not that much. However, for the FMV SSS 226 with 6 seconds runtime, this might be important. Typically, as a curtain is completely sealed, so you don't have holes and don't have permeability. Speaking about permeability, also for the isolin and ortholin, permeability can be defined. One of the drawbacks of isolin and ortholin is that the shear modulus is generally too high, and due to that the shear is not described properly. We will give some examples of that in the following slides. This wrinkling or this shear effect, as I said, is well captured in fabric shear. You are able to define non-linear functions for your thread directions. You can define unloading and hysteresis for that as well. You can describe the shape of your airbag much more accurate than with isolin ortholin. Also for fabric shear, you can apply permeability models. The permeability models will be interesting in another presentation. Here you see an example of fabric shear. It's a driver airbag. And you see here the top and the bottom. The top is 45 degrees rotated with respect to the bottom. As you can see, there's occurring a sine wave at the stitching. From the top view, the driver airbag still remains round. However, if you're going to apply the directions on top and on the bottom in the same direction, you will get from the top view a more square looking airbag. The sine wave is now gone. And generally, these directions are defined with respect to the reference mesh. Here you see in comparison with respect to an experiment. On the right side you see the fabric shear, and there is a sign occurring. The left is isolin or ortholin, and there you see there is no sine wave occurring. This is because of the shear modulus. Obvious, this will affect your results, because the volume will be different, and the pressure might be different as well due to that, and also the moment of contact, or the way it slides off the airbag, potentially. So, for that reason, we recommend to use fabric shear. As said in the previous presentation, you can apply tethers. Tethers are used to control the shape of the airbag in the deployed state. This can be done in two ways. One is the 1D approach, or the more detailed approach with membrane elements. In this picture, you see an example of the line 1 element. We recommend to use material strap for that, in combination with truss. If you like, you can even define rupture failure. This way, with straps, is generally used for skilled airbags because they are simple to model. You can change the length of the line 2 element, and for that also controlling the shape. If you would like to use membrane elements to specify a tether, that's also possible. If you would like to use failure or to define failure, you can make use of interface elements. I would like to go back to the straps for a little bit more explanation on the mass specific and the damp curve values. Let me start with the damp curve. It's a value typically between 0 and 1. We recommend to apply a very high value. Reason for that is that the straps behave like a rubber band. They are elastic. Well, of course, in real, that's not the case. By defining a high damping, you damp out these rubber band oscillations. And that's also related to the mass specific. The mass is only at the end of the line 2 elements. Well, that's of course in real not the case, because you have real fabric. So then there's only a tiny part of the fabric tethers which is making contact with the head. If you define a high specific mass, it means that you have high masses in the region where the head can contact the airbag. If this mass is too high, you will observe high peak or high noses in your acceleration results, which of course are not correct. For that reason, the mass specific has to be low. An example like given here is a correct value for that. That brings me to the end of this presentation. Goodbye.